Metallurgy feels random until you learn Ellingham diagram. Most students skip this graph, then lose easy JEE marks. Hello students, let us start. Ellingham diagram. First of all, Ellingham diagram is used in metallurgy to predict which metal oxide is more stable, which reducing agent can reduce a metal oxide, at what temperature reduction becomes possible. Very important, these 3 points, remember. It is the graph between Gibbs free energy, standard Gibbs free energy versus temperature. For example, if metal oxide and decomposition giving metal plus oxygen, decomposition reaction where delta G is positive. Delta G is positive meaning non-spontaneous reaction which cannot occur on its own, some extra energy required, heat energy required for above reaction. The same reaction if I reverse it, metal plus oxygen gives metal oxide, this reaction is spontaneous where reaction delta G is minus, you can say negative value. Whenever negative value given for a reaction, reaction is feasible. Positive value, reaction is not so easily occurs, some external force required. If delta G naught is more negative, you can consider even it as delta G naught standard values. So if delta G naught is more negative, oxide formation is more stable. Remember, more is the negative value of delta G naught for a reaction, oxide formation is more stable. The oxide whose line lies lower in the diagram has. This point is most important, it decides entire questions of Ellingham diagram. The oxide whose line lies lower in the diagram has greater affinity for oxygen. Whichever is lower in Ellingham diagram, whichever oxide having lower line in Ellingham diagram has greater affinity for oxygen, more stability, those metals can remove oxides above it. For example, if I take two graphs, like here there is one graph, here also there is one more graph. Here A, here think that there is BO2 here. Think that there is A graph here. So oxide whose line lies lower in the diagram has C. A line, it is lower in the diagram. So now overall concept, the theme concept here it is the lower line having greater affinity for O2, these metals can remove oxides above it. Meaning can remove oxides, can reduce oxides, you can specify here like this, can reduce oxides above it. Overall, whichever, for example, if I take here line A, is it below BO2? So now this particular metal can reduce BO2. Simple concept, whichever line is below in diagram, particular element having more tendency to reduce above oxide. Here see, for your reference, the graph given, that is between delta G naught and temperature graph given. See here, see, graphs are, some are straight line, some are after some time intersection point, diversion. So different graphs given. How we need to relate it, see here, how we need to read it. See, whatever here intersections, this you can see, sudden break in, after some time break in the value. So these values here breaks, wherever there is intersection points, those are phase changes, melting point, boiling points. I am showing, see here, it is for reference, no need to remember this entire graph, just reference purpose I gave. See here, in above diagram, Al2O3 line lies below FeO line. I am showing, see here, Al2O3 line. Al2O3 line, where it is, see, Al2O3 line, this is Al2O3 line, this one, if I see Al2O3 line, lies below FeO line. Where is FeO line? FeO line is, see here, here, it is FeO line. Al2O3 line is here. FeO line, this one. So Al2O3 line is below FeO line. So hence Al has greater affinity for oxygen, hence it can reduce. So oxygen is acting as reducing agent. It can reduce Fe2O3 and convert Al2O3 and plus Fe. Thermite process, we already discussed this reaction. Thermite process. Okay. So here, whichever point in lower in the Ellingham diagram, that particular metal having tendency to reduce above oxides. For example, see here, Al2O3 is below MnO. So Al2O3 can reduce MnO also, or aluminum can reduce MnO. So whichever is below in series, such metals having more tendency to reduce above oxides. Only one line you remember, element whose graph is below in Ellingham diagram having more tendency to reduce above oxides, like this. As temperature increases, delta G increases. Here we are taking the standard value only. Delta G increases. most lines slope upward. As temperature increases, delta G naught increases. See, most lines slope upwards. It is moving like this, most lines. Why? Slope upward, because delta G is equal to delta H minus T delta S. Delta G is equal to delta H minus T delta S. If temperature increases, delta G naught value increases. Next, sudden breaks in line indicates. See here, delta S is negative here, remember. Delta S is negative here. Why delta S is negative? Because if metal oxide is formed like MO2, if it is metal oxide is formed, entropy decreases. Whenever two elements like M plus O2 giving MO2, entropy decreases. Two elements combining to form here one compound, overall entropy decreases. Entropy decreasing means delta S is negative. So delta S is negative, it becomes positive, then temperature increases, delta G naught increases. Here you can specify all are standard state. Delta G naught increases. That's why your delta G naught increasing. So keep in mind, delta S is negative here. Sudden breaks in line indicates melting, phase change or change in allotropes. See here, sudden break in line. Here you can see sudden break in line or sudden diversion of the line. Sudden, see, tilting it is. There those points are melting points, phase changes, change in allotrope, like that. Some reductions occur only at high temperature. Ellingham diagram predicts the temperature. Few reactions occurs only at high temperature. Even that particular temperature predicted by Ellingham diagram. Lower line removes oxygen from upper line. This particular line enough to solve questions. See here now one question. Carbon monoxide is more effective reducing agent than carbon below 983 Kelvin. But above this temperature, the reverse is true. How would you explain this? Carbon monoxide is more effective reducing agent than carbon below 983 Kelvin. See, here there is 983 Kelvin. So below 983 Kelvin in this zone they mention carbon monoxide is better reducing agent than 983 than carbon. See, below 983, like this particular zone. See here, carbon monoxide line is C. Carbon monoxide line is below this carbon. Below 983, once again observe properly, below 983, this one, below this. Carbon monoxide line is below carbon line. Carbon monoxide line, this one. Carbon line, red color line, think that. So now whichever is below in the Ellingham diagram, which is having more affinity, which is best reducing agent. So below 983, carbon monoxide graph is below carbon. But above this temperature means this particular zone. Above this temperature, see here now. Above this temperature, which is below, above this carbon graph is below, this one. Carbon monoxide graph is above. That's why carbon is best reducing agent under high temperature, lower temperature conditions, carbon monoxide. That's why in some case we used carbon monoxide reducing agent, some cases carbon. So higher temperature carbon, lower temperature carbon monoxide. That's what linked with metallurgy till now, whatever we discussed. Okay, that's what explanation given here. Important alloys list also attached here. You can see brass, bronze, gunmetal, bell metal, solder, alnico, nichrome, invar. These are most important alloys. Repeated last questions in JEE. So all these alloys important list, previous last questions list given here. You can refer it properly and understand those components. Use is not so important. Mainly components composition remember here. Key points about extraction of metals. JEE process used for refining of silver. Here some important statements given, important questions. So no in-depth concept here, you have to remember all these statements. JEE process used for refining of silver. Electrolytic reduction mainly used for sodium, magnesium, potassium, calcium and aluminum, etc. Downs process used to manufacture sodium. Pooling process for refining of copper and tin. Distillation for zinc, cadmium, mercury. Liquefaction used for lead, tin, antimony, bismuth, mercury. Mons process for nickel. Van Arkel method for titanium, zirconium. Both are referred as vapor phase refining. Zone refining for silicon, germanium, boron, gallium, indium. Cupellation, removal of Pb from Ag. Kroll-Collen process, titanium. Electro refining of metals, copper, silver, zinc, tin, lead, aluminum, nickel, chromium, mainly used under refined by these methods. Blister copper, copper plus SO2 gas trapped in it. Reduction of metal oxide with carbon at high temperature is smelting. Hall's process, concentration of bauxite with red impurities. See, Hall's process we use in extraction of aluminium. So Hall's process, bauxite is ore of aluminium. Hall's process where we use Na2CO3 chemical. So here this particular Hall's process we use when bauxite having red impurities like Fe2O3. Even Bayer's process where NaOH is used. Bayer's process also used to remove red impurities present in bauxite, mainly in aluminum extraction. Serpex process, SERPECKS, Serpex process where carbon is used for white impurities. For the removal of white impurities, SiO2, we use this method. Azurite, 2CuOH twice CuCO3, malachite, CuOH twice CuCO3. Formulas. For high grade ores of copper, pyrometallurgical process is used. See, pyrometallurgical process is dry process where heating required. Low grade ores meaning where impurity of carbon is more than, greater than or equal to 4%. For high grade ores. For here impurity of, not impurity, it is copper it is. Copper greater than or equal to 4%. For low grade ores of copper, hydrometallurgical process is used. Hydrometallurgical process meaning that is involved in dissolved in solution. In solution form we use this method, here dry form, heating form. Slag formed during extraction of copper is iron silicate, and iron extraction, during extraction of iron, the slag formed is calcium silicate. Slag formed during extraction of copper is iron silicate, extraction of iron is calcium silicate. So during extraction of copper, this particular mixture is formed, Cu2s plus Fes, which is known as copper matte. You can refer it as copper matte. Wrought iron, it is having 0.1 to 0.25 percentage of carbon, steel 0.25 to 2% carbon, cast iron 2.6 to 4.3% carbon, pig iron 2.3 to 4.6% carbon. Purity point of view, wrought iron purest, then steel, cast, pig iron. Purity meaning more carbon content, less purity. Steel making process occurs in Bessemer converter, pear shaped converter it is. Quenching or hardening of steel meaning, here it is steel is hard and brittle. Steel when heated to 700 to 800 degrees Celsius cools suddenly. This process known as quenching or hardening of steel. Annealing of steel, to get soft steel we use this method. Steel when heated to 700 to 800 degrees Celsius cooled slowly. This process known as annealing. We will get soft steel. Cooled suddenly or cooled slowly. Tempering, hard but brittleness disappears. So during this process, you can say tempering, hard but brittleness disappears. Tempered steel meaning hard but brittleness disappears. Nitriding, steel here on heating around 1000 Kelvin in presence of ammonia, hard coating of iron nitride is formed. Hard coating of iron nitride is formed. Nitriding. Case hardening, steel when on heating along with charcoal, that is quenching in oil, directly dropping into oil, thin coating of hardened steel developed. Tin, main commonly used ore SnO2, impurities of Fes, Cus, SiO2, FeWO4, magnetic separation we use, roasting of copper sulfide, iron sulfide, carbon reduction method, finally pooling process for purification. Lead, here PBS commonly used ore, concentration by fourth flotation, roasting, self reduction, finally liquefaction. Magnesium, ores here carnallite, magnesite, Downs process, electrolysis of molten MgCl2, CaCl2 plus NaCl, anode is graphite, cathode is iron. Okay, different important statements I gave here, which are repeatedly asked JEE mains and advanced questions. Properly pause the video, observe it. Next, JEE mains online 2020 question. See question here. According to the following diagram, A reduces BO2 when the temperature is. Only see such graphs to solve question, only one simple trick. Whichever graph is below, or whichever element line is below in graph, particular element can reduce above oxides. So now you see here till 1400 Kelvin, till this point, the graph of B that is below AO2, the graph of B is below A, right? So here what they mention, A reduces BO2. So to reduce BO2, A graph should be below BO2. To reduce BO2, according to principle, whichever element having graph below, whichever graph lies below in Ellingham diagram, such graphs, such elements can reduce above oxides. To reduce BO2, A graph should be below BO2. When it is below BO2? After 1400 degrees Celsius, it's not below BO2. Less than 1200, less than 1400, greater than 1200, but less than 1400, no. After 1400, the graph you see, the graph of BO2 and A, if we compare, A graph is below BO2. So we need such condition where A graph should be below BO2 to reduce BO2. Hence, answer should be greater than 1400 degrees Celsius, because after 1400, A graph is below BO2 graph. Next, the third statement regarding the given Ellingham diagram is, at 800 degrees Celsius, Cu can be used for the extraction of zinc from zinc oxide. Cu can be used as extraction of zinc from zinc oxide. So observe it, all the, okay, in graph if you see here, at 800 degrees Celsius, for example, if I take it as 800, think that here 800 degrees Celsius, it is given in the question, 800 degrees at this point. At this point, at 800 degrees Celsius, copper can be used for the extraction of zinc from zinc oxide. So meaning copper can act as reducing agent according to them. So where is copper? Copper is here, copper line. Zinc oxide line is here. So in order to reduce zinc oxide by copper, if in order to reduce zinc oxide, copper line should be below zinc oxide, but here copper line is above zinc oxide. So which is not true. Which is not true. At 500 degrees Celsius, coke can be used for the extraction of zinc from zinc oxide. At 500 degrees Celsius, you see here now, 500 degrees Celsius, coke is carbon. Where is carbon line? Here. Carbon line is here. At 500 degrees Celsius, at this point, coke can be used to extract zinc from zinc oxide. See, at 500 degrees Celsius, coke line is above zinc oxide. This 500 degrees Celsius, coke line is above zinc oxide. After 800, it crossed below. After 800, but below 800 at 500 degrees Celsius, carbon line is above zinc oxide. Only one parameter, to reduce above oxide, the element graph should be below particular oxide. To reduce zinc, the carbon graph should be below zinc. So here also not possible. Next one, coke cannot be used for the extraction of copper from copper oxide. Coke cannot be used for the extraction of copper from copper oxide. Let us see now. Coke is carbon here. You cannot use extraction of copper from copper oxide. Why? Here graph is below the copper. Line of carbon that is below the copper. So it can reduce. So here it is. They mentioned cannot be used. Cannot be used also here false. We can use because the line of carbon is below copper oxide. Next, at 1400 degrees Celsius, aluminum can be used for the extraction of zinc from zinc oxide. At 1400 degrees Celsius, one example I am taking here, 1400 degrees Celsius, more than, for example, here there is 1400, think that. At 1400 degrees Celsius, what they mention, aluminum can be used. Yes, aluminum is below zinc oxide only. Aluminum line is below zinc oxide. So it can reduce it. So answer is fourth option. Next you see, J advanced PYQ here. Select the correct statements about the plot. So now here observe it. T1 and T2 are the melting point of boiling point of Mg respectively. See here T1, T2. Already we discussed above, wherever there is tilted line, wherever there is slight intersected line or slightly increasing line, wherever there is break in the line. See here these points are broken lines. T1, T2 are melting and boiling point of magnesium only. Yes, it is those phase changes. T1, T2 are melting points and boiling points of MgO. It's not oxide every time, remember. It's not about oxides. It's only related to metal. Those are related to metal. Next, reduction of MgO by coke is possible above T3. Reduction of coke is possible above T3. So, reduction of MgO by coke is possible above T3. Yes, see, about T3, coke graph is below MgO. About T3, after crossing temperature T3, the coke graph is below MgO. Yes, hence it is possible here. C. A, B is incorrect. Mg can be extracted from gaseous products by rapid cooling. Yes, under high temperature conditions, Mg exists in vapor form, which can be extracted from gaseous products by cooling. It is also correct. A, C, D. Multi-correct answer, J advanced PYQ. So here it is A, C, D. correct here in the case. Okay, so that is about JEE Advanced PYQ. Yes, I hope all the questions clear to everyone. For more updates, follow the channel. Thank you everyone.